now ready for the third talk of this session. So the title of the talk is Quantum Separation Logic, a framework for local reasoning of quantum programs. And Xuan-Bach is the speaker for this talk.
Okay, yeah, thank you for the introduction. My name is Xuan-Bach from Singapore, and today I will present the paper, Quantum Interpretation of Separating Conjunction for Local Reasoning of Quantum Program based on Separation Logics. This is a joint work with Shang-Wei, Junsun, and David when I was working at NTU Singapore, and uh, it's midnight in Singapore, so please bear with me. In this talk, I will discuss about how we can apply local reasoning for quantum computations. Furthermore, we aim to make the reasoning more user-friendly and intuitive. It's well known that quantum programs are very difficult to write, understand, and verify. And here is what a typical quantum program would look like at the circuit level. And there are several components in a quantum program. We have the qubit, which store the state of the quantum programs. We have the quantum gate, which transform the state of the qubits. And we have measurement, where we measure the state of the qubits. Although this program look quite simple, it's almost impossible to understand what is going on. And one may try to take the circuit and rewrite it using some intermediate language like this, but it doesn't really actually help us to understand the programs. Yes. The main reason why quantum programs are written in such a cryptic way is to make use of the extraordinary power of quantum computations. So let me illustrate this point. In the example, suppose that we are given a function f from 0, 1 to 0, 1, and we say that f is constant if f0 equal to f1, and f is balanced if f0 not equal to f1. And our task is to determine the type of f. Normally, right, we need to evaluate both f0 and f1 in order to conclude the type of f. But we use those algorithms for quantum computations, then we only need to evaluate f1s, and thanks to the superpositions. And here is the algorithms. On the left, we have the code, and on the right, we have the corresponding quantum circuit. And in order to have an idea on how it works, let me first explain the key concept behind quantum computations. In classical computation, we have bit which can have the state can be either 0 or 1. In quantum computation, we have the smallest information unit called a qubit, and its state can be both 0 and 1 simultaneously. Sorry? Can you hear me? Namely the superpositions. These very unique features allow us to parallel the computations, and therefore it can potentially yield exponentially computation speed up. And the key idea behind many quantum algorithms can be summarized by a quote from Scott Aronson, a professor from Texas University, that a good quantum computer algorithm ensure that computational paths leading to the wrong answer cancel out, and the paths leading to the correct answer reinforce. If we go back to our example and see how this principle can apply. So initially, the qubits are in the classical state zeros. And so the first step of the algorithm is to repair the superpositions. And then we can apply f one time over the superpositions. And finally, we decode in the superpositions and measure the qubit to determine the type of f. So in our paper, we used the following programming language to write quantum programs. On the first line, we have everything is standard. We have skip, classical assignment, conditional statement, sequence. And on the second line, we have statements for quantum computations, such as qubit allocation and deallocations. So for qubit allocation, right, uh, the statement here means that we create an array of qubits of size E and initiates their state to zeros. In contrast, the dispose statement frees the entire qubit array. And before discussing the other two quantum statements, let me briefly explain how we express the state of a qubit in the papers. So in these expressions, we have Q B to be the qubit ID, and the normalized vector alpha 0 plus beta 1 written in Dirac notation represent the superposition of the qubit, where alpha beta are complex coefficients. So in general, the state of cubic in mix, meaning that it is a probabilistic ensemble of pure state, which I just showed you in the previous slides. Uh, but in this work, we break down the mixed state into a pure state that with their probabilities. And so here how we represent the quantum state, where the map to predicate in the blue color represent the pure state. And the row in the green colors on the left is the probability associated with the state. And for convenience, if the probability is 1, then we can remove it. We think such representation is more appealing to human intuitions, and more importantly, it enables local reasoning. I will explain it later. But there are a few disadvantages. For example, we lose expressiveness and completeness for reasonings, particularly when we want to reason about the entire mixed space. So in our language, we have the quantum statement for cubic transformations here. And semantic-wise, it basically just linear transformation of over the vector space. And here is an example. Suppose that the cubic Q have the state 0, which can be expressed by the column vector 1, 0. And the Hamadat get, which specified by the unitary matrix hashed. Then the Hamadat get transform the state of Q into the superposition of 0 and 1 on the right. And finally, in our language, we have statement for measurement, where we measure the classical state of the qubits and assign the result to classical variables. So X here is a classical variable. In detail, after the measurement, right, the superposition of the measured qubit is collapsed into one of the classical states, and the probability of each outcome is multiplied with the probability of the state. And here example, suppose that we have a qubit Q in this superpositions with probability 1/2. Then after the measurement, we have the state of Q to be either 0 and 1 with equal probability of 1/4. And so that's all for the description of our language. And here just to show you an overview of our inference rules for the quantum statements, with it is very general, and they can handle multiple qubits in the transformation and measurement, even including the entangled case. And you can find more detail in the papers, of course. And but most importantly, well, in the paper, we propose the frame rule to support local reasoning for quantum computations. So here is our rules, and you can realize that it's actually identical to the frame rule for heap manipulated programs. So briefly speaking, right, the rule says that if we have the triple BCQ, then we can attach the frame predicate f into the pre and the post conditions of the triple, given that the program C does not modify the free variables in f. So recall that for heap manipulated programs, memories are resources, and the star represent the joint memories. But in quantum computations, the interpretation is different. So we treat qubits as resources, and the predicate f1 star f2 means that the qubits in f1 and f2 are disjoint, and their state can be expressed independently, kind of, yes. So what do I mean by express independently? So here in examples. So uh, here we represent how we represent the combined state of multiple qubits, or more precisely, 2 qubits. So technically speaking, the combined state is just a normalized vector in the tensor space. Uh, for 0, 1 here, it actually is a shortcut for 0 tensor with 1. And if we can factorize the combined state of Q1 and Q2 into the tensor product of two normalized states S1 and X2, then we can separate the state of Q1 and Q2. Furthermore, the probability is split via multiplications into row 1 and row 2. And notice that the factorized vectors and the probabilities are not necessarily units and can be differed by a constant. So for example, if our state Q1, Q2 is 0, 1, then of course we can factorize it into 0 for Q1 and 1 for Q2s. Another factorizations is we have I0 for Q1 and minus I1 for Q2, where I is the imaginary numbers. And both factorizations are semantically equivalent and do not affect the correctness of the programs. So here is a more complicated example. Suppose that we are given the following superpositions of Q1 and Q2. Then first we can factorize the first 2 terms and the last 2 terms in the superpositions. And then we realize that both products appear to share common factors in blue colors. And so we can group them together. And by doing that, we successfully separate the state of Q1 and Q2. Unfortunately, not every combined state can be factorized. So here is an example of 2 qubit Q1 and Q2 in the entangled Bell state. And one can show using proof by contradiction that no factorization is possible. Semantic-wise, we model our quantum heap to be the triple of probability rho, quantum state Q, and classical sigma with map classical variables to value. And given another heap H ram equal to rho ram Q ram sigma, in which the quantum state of Q ram is disjoint with Q, then the disjoint union of H and H ram is defined to be the heap with probability rho time programs, quantum state Q tensor with Q prime, and the classical state sigma. So let's apply the framework to verify those algorithm at the beginning of the talk. So for demonstration, I also include the statement for qubit allocation and the allocations. And here are the specification of our program. So the preconditions of our program is M with basically the empty heap. And the both conditions here which indicates that Fe constant if V is 0 and Fe balance if V is 1, where the classical variable V store the outcome of the measurement. And also in the both condition, we have the empty heap because of the allocation in the end. So starting from the precondition M, we apply the allocation rule to to derive the boss condition of Q0 and Q1, in which their state are initiated to 0 and therefore are separable. And notice that in the boss condition, we also have the sign conditions, which basically say that uh, the length of the array Q is 2 for accounting purpose. We then use the frame rule to do local reasoning for the transformations of Q0. So after applying the Hamadat get, the state of Q0 is transformed from the classical state 0 into the superposition of 0 and 1. And similarly, the transformation of Q1 can be reasoned locally, where we first use the poly-x get to flip the state of Q1 from 0 to 1 before applying the Hamadat get to obtain the superpositions for Q1. And now we combine the state of Q0 and Q1 in order to apply the transformation of UF for the evaluation of F. And after the transformation, the state of Q0 and Q1 can be factorized and therefore are separable. And this allows us to apply local reasoning for Q0 after that. So after applying the Hamadat get, the state of Q0 becomes 0 if f is constant and 1 if f is balanced. Accordingly, by measuring Q0, we are able to determine the type of f. And finally, we combine the state of Q0 and Q1 and apply the deallocation rule to obtain the empty heap M. So to wrap up, in this work, we propose a reasoning framework for quantum computation with the frame rule for local reasonings. And the key idea is to represent the quantum state, a pure state with probabilities, which can enable separability via tensor factorizations. And for evaluation, we apply our framework to verify various quantum programs such as the Jozsa algorithms and Rover's algorithms. And for future work, we plan to work on the completeness of our framework and extend the framework to reason about quantum entanglement. We are also interested in mechanizing the framework and developing decision procedures to support automatic reasoning. So that's it. Thank you. So yeah.
Okay, so thank you for your talk. Are there any questions in the room? Okay, I have one question, which is the talk just before yours also was
Yes.
considering separability as a key component, doing it in a type system and with assertions instead. I wonder if you could compare and contrast your logic-based approach to that one.
So uh, so I think for the previous talk, right? I think uh, the the main focus is the pure state. Even I'm not mistaken, right? So, but in our framework, we actually also consider kind of factually mixed state, uh, and and for the type system, and it actually they're actually two different things, I guess. For our framework, it actually focus on reasoning about the correctness of the program. When the previous talk, I think, for focus on the the type of the of the quantum system.
Okay, I guess I'll just to follow up what I was thinking about. You know, a type is characterizing. You can consider it a more abstract logical formula. There's a lot more semantics baked into that type, and you could imagine those types being embedded in a logical system such as the one that you're developing, where you can use easier reasoning capabilities when necessary. But maybe in the cases that the twist system required that static analysis or the dynamic verification, maybe your system would come into play. That's what I was thinking of as a possibility.
Yes. Yeah, maybe.
Okay.
Yes.
Any other questions from the room? Okay.